review these problems, I'm going to show you how to do them, and you can also check the answers in the back of your book. But we'll start with number 3 on page 226. Mammotype. Now this has to do with blood types. Now remember that there's 3 alleles for blood types, and it's an example of multiple alleles. And there's also an example of codominance, where if you have a heterozygote, you see both traits. So the question gives you a couple examples, and the reason that you know that the dad is a heterozygote and the mom is also a heterozygote, they both carry the recessive trait. The reason I know that is because the only way they have a child with type O is if the genotype was little I and little y. And if you did a little Punnett square of their mating, you could actually see how this all works out. And you separate the alleles of the dad over here, and the mom over here, and then you do your Punnett square. Type B, 25% type AB, 25% type B, 25% type A, and 25% type O. Okay, that should be the answer. And this, what tells me that they're both carry the recessive trait is that they have a child that's heterozygous. Okay. All right, let's move on to question 6. Question 6, you need to look at the data in that table. And we'll work through it. Okay. So it shows you the data for the flower position, the stem length, and the seed shape. Okay. And it also tells you we know what the parents are like. The parents are heterozygous for all 3 traits. So one parent would be this, and then since it's allowed to self-fertilize, it will also be this. Okay. And then basically they say, what are the probabilities for a certain type of offspring? And so the probability for the offspring in letter D was homozygous for axial, would be this, tall, homozygous, and heterozygous for seed shape. So now the question is, what is the probability that if these two self-fertilize, this one and this one self-fertilize, that they're going to get an offspring like this? And you need to break it down, and you got to remember, and we're assuming that all these are on separate chromosomes and they assort independently. So let's take a look at just the A. And I'm going to just break it down for the A, and then hopefully you can figure out the rest. But the A, you do little mini Punnett squares for A. So A would be, for this one, be this. So I did a little mini Punnett square for these two mating. Okay? And basically what you would get is this. And you guys should all be familiar with this. And what is the probability of this happening right here? We know that that's going to be 1/4. Okay. Well, if you did that for the T's, you'd also get 1/4. If you did that for the R's to get a heterozygote, you know it would be 1/2. You multiply those all together, and the answer should be 1/32. Okay. And again, the key is looking at these individually. They assort independently. They do not influence the other ones. And we're moving on. Okay, now we do question number 8. In some plants, true breeding method gives pain. So they're showing you now that this is an example, at least for this gene, this loci is going to show examples of incomplete dominance. And so for example, if you cross this with a white one, now homozygous white, you're going to get the offspring is going to be pink. We know that's incomplete dominance because it is not red, it's not white, but it's something in the middle. So it's this blend. So that's incomplete dominance. But they also throw you a curveball. They say that we also are looking at the same characteristics for axial that are described in the table in number 6. So basically what they say is, take an axial red, true breeding. So axial red, we know it's this. Axial red, it's true breeding, and we know that axial is dominant because it says it in the table, and we know that that's going to be true breeding red. And we're crossing it with a terminal white. So it's going to be little a, little a. Okay. So what are the examples in the F1 are pretty simple, and hopefully you guys can figure this out. That this individual is only going to throw out one gene for each character. So this one is only going to have in all its gametes a big A and a CW. Okay, in all its gametes. And then this one's going to have, I'm sorry, CR in this one. Whoops, CR. And in this one, you're going to have a little a and a CW. So when these come together during fertilization, you get this hybrid. It's hybrid for the A's. And you're going to have a pink flower. I'm just going to do it all in black here. So we're going to get axial. Pink. Okay. Hopefully you guys get that. Now I'm going to erase this. This should be pretty simple. 100% of this. Now it throws you a curveball. What is the results in the F2? Well, the F2, I'm going to write these up here. You have this individual, this axial pink individual, and we should know that F2s self-fertilize. Okay? And this sets us up for a dihybrid cross. If you're not familiar with dihybrid cross, you need to look this up. Now this won't show the 9331 patterns because we're dealing with incomplete dominance at this location. So, but you still need to set up a Punnett square. This could be a large Punnett square, a 4x4 Punnett square. And you need to determine all the gametes, all the possible combinations of gametes that this one will have, and all the possible combinations of gametes that this one will have. And so basically you're going to get this. Capital A, C, red, capital A, W, little a, red, little a, white. And you're going to do the same going down this way. Capital A. So I'm gonna just keep it consistent. This is going to be red. There, W, red, white. Now, what we get here is then you put these two together, you're going to get big A, red trait, homozygous for that. You're going to get big A, W, a pink, axial pink. You're going to get let's say capital A first, and a red individual, axial red, and then you're going to get a heterozygous at the axial, and you're going to get red. Well, you're going to need to start tallying these up and go through this whole 4x4 Punnett square to get the results. And the results are in the back of the book. I'm not going to go through all this just to save time. But you do need to complete this whole table and then tally up all the possible combinations that you'll get. Okay, so that's number 8. Let's go through number 9. Okay. Number 9. Sesame seed lights. Okay, number 9. Now it tells you that it writes down the conditions that capital P equals 1 pod. Lowercase p equals 3 pod. And L equals normal. Little l equals wrinkled. Okay. Now, you have 2 parents. Now this one's kind of tricky. It doesn't tell you the parents, but it tells you the offspring. And so let's write down the offspring. So in the offspring we have 150. We have 150, 1 pod normal. And we have 147, 1 pod wrinkle. Right? Then we have 51, 3 pod norm. And we have 48, 3 pod wrinkle. Okay. What were the parents of this cross? Well, the key to this is you need to separate out this characteristic from this one. You need to look at these independently, like little bitty Punnett squares happen. So let's count up let's just look at the 1 pods and determine what were the parents if we were just looking at 1 pods. So 1 pods let's total all up to 1 pods. We have 150 right there, and then we have 147. There were no other 1 pods, so we're going to get 297 1 pods. And then let's tally up the 3 pods to get 51 and 48. We're going to get 99. 99 3 pods. Well, if you look at this, wow, let's round them up. This is a 3-to-1 ratio. Holy cow. So, at least for the P's, we know the parents had to be this. Big P, little p, and we're going to leave this one blank. And we're going to have the other parent also had to be big P, little p. Because if you have heterozygotes, you're going to get, and you cross them, you're going to get a 3-to-1 pattern. And the 1 pod's dominant over the 1 pod's dominant over the 3 pod. Okay, so now let's take a look at the wrinkles. And I'm going to erase this right here. Let's tally up all the leaf shape. Let's see how many normals we have. We have 150 normals right here. And then we also have 51 normals. So we have 201 normals. And then now let's take a look at our ranks. We have 147 here and 48 here. 147, 48 here. That gives us 195. Holy cow! This looks almost like a 1-to-1 ratio. Well, what kind of cross will give us a 1-to-1 ratio? And I'll let you guys figure this out, or you can fill out the Punnett square, but I'll set it up for you just to assure you this, that one individual had to be homozygous. Oops, and we're doing L's, sorry. One individual had to be homozygous recessive, and another individual was a heterozygous. And if you fill out the Punnett square, you're going to get 50-50. And so one individual was a heterozygote, and the other one was recessive. So that shows you how to do that. And again, the main point is, these are on different chromosomes. They assort independently. Count up all the ones in one, and then count up all the other ones in the other. So count up all these, assume that they're just all by themselves. Count up all these and assume they're all by themselves. And they assort independently. They're on different chromosomes. Okay, we'll keep moving. Okay. So let's stop this and we'll do another one. We'll do 10 thread on another one.